Okay, let's get started. So in the previous class, we were seeing how multi-layer perceptrons function. So we saw that we have a input series or input features. All these input features will be connected to a layer of perceptrons. So a single layer consists of vertically stacked perceptrons. Each perceptron is each perceptron is getting information from all the input features that we have. So this is called fully connected uh, layer structure. So you can also say that each and every single neuron is connected to each and every single neuron in the next layer. So if we have three neurons in this layer, all the four neurons are connected. Each single neuron is connected to all the four uh, neurons in the previous thing. So similarly, each and everything is connected to every node in the next step. So this is called a fully connected network called multi-layer perceptron. So since there are different layers of vertically stacked perceptrons, we'll call them multi-layer perceptrons. So uh, these parts in these layers in middle are called hidden layers. The green part here is called the input layer, and the yellow part here is called the output layer. This is the whole structure of a multi-layer perceptron. So you can calculate the number of connections between each and every layer. And as we increase the number of perceptrons, the total number of connections will increase exponentially. Since each neuron is connected to all the neurons in the previous layer and is connected to all the neurons in the coming layer. So now let's see uh, uh, how to reduce the total number of connections and still retaining the information processing time. So generally we have two kind of neural networks. We can call them convolutional neural networks and recurrent neural networks. Convolutional neural networks are mainly used to process image information or structural data, and recurrent neural networks are mainly used to process sequential data. It's not necessary that CNN be used only on images and RNN on time series. We can also use CNN on time series and similarly RNNs on images. So when the whole uh, uh, industry started, CNNs have been picking up pace in doing most of the required things like classifying and detecting different parts in an image, and RNNs have been used to do recommender systems or time series classification. But a new form of structured new structure called transformers is slowly taking over the CNN part that can be used to classify images. So it depends upon the task that you are using. Say, suppose we'll go through how CNN works. Say, this is an image we have, and each any image is consists of pixels. So, suppose we have these pixels available for us. So each box here represents a single pixel, and suppose we have a 3x3 kernel.
అంటే ఇది ప్రింట్ అయితే పనికి వస్తుంది ఆన్లైన్ కోర్సెస్
suppose we have this, so each pixel has some value from 0 to 255. So this is 0, this is 1, this is some 42, say this is some 254. So each pixel has different values in them. So this can be some 7, this will be 6, 4, some values in each pixel. So now we have a 3x3 kernel here. So what does a 3x3 kernel has is it has the weights attached to it. So in previously, while doing our linear regression, we had a y dash equal to some weight w0 plus x1 with w1 and so on till xn wn. So each value, this W0, W1, W2, these are all the weights attached to each neuron. So previously we had one neuron will take all the information containing, and it will do the cross dot product and will give us the output. This output will be sent into some non-linearity and we'll get the prediction. So this is the same similar stuff, but instead of taking the information from the whole features, say here we have 1, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So we have a 36 pixel grid here. So we can say that there are 36 different features for our image. So if we attach this to a single neuron, this neuron will get information from 36 different features. Rather than that, we are trying to compress or reduce the number of connections between each neuron. So what we do is we create a 3x3 kernel. This each kernel will have some weight W0, W1, similar to the perceptron here. But here we are restricted to only 9 weights, 2 and W8. Or you can say that there are W9 and some W0 will be our bias. So yeah. So now we take this kernel, we and do our cross product with this. So the first pixel will be information will be multiplied with W1. This will be multiplied with this. This will be multiplied with this. Similarly, so initially, so we'll do the this dot product with these 9 numbers with this neuron, and we'll get some output value. So say some 7 is our output value. We took the weights here and multiplied with the feature available here and added all the 9 values, and we got a number 7. Now we'll take this kernel here and we will do a stride. Stride is nothing but moving up one pixel next. So previously we took first, second, and third columns. Now we'll take second, third, and fourth columns, and we'll repeat the same process. Now say we got some value 6 here after doing all the 9 multiplications and summation. And now once again we can move this kernel. So now we move it one more column. So we'll get some value, say 8. After one more move, we will reach the last. So we have some value 6 here. So you saw with the stride equal to 1, we are moving each column at a time. if we are doing stride equal to 2, we'll skip 2 columns at a time and jump. So this is just now after that, if we have one stride, we'll go to the next row. It will go here. So this part will be taken. So if we have stride 2, then we'll jump 2 rows down. So we'll go like this, we'll jump, go like this, and again jump and go like this. So after doing this, say with the stride 1, if we have a 6x6 image and 3x3, we will get 4 outputs. So similarly, here we'll also get some 8, 1, 3, 2, some values, 6, 3, 2, 1, 1, 0, 3, some values like this. A 4x4 grid will get a 4x4 grid. So this is a new set of information that we have. So now after this, this is like a single perceptron. We went through all the data available with only 9 weights. Previously, if we have wanted to go throughout the image, we needed 36 weights. Now we used the 9 weights, and we are using the we are recycling these weights to go through different parts of the image. So not only this, we can also have more number of kernels that are the same. Excuse me. They are of the same size. So we'll use the same kernel and do the strides accordingly. Let me show you the final structure. So yeah. So here is our input image. We have one convolutional layer. So one convolutional layer can consist of many number of these kernels. So previously we had many number of vertically stacked kernels. So vertically stacked neurons. So here we can have different number of kernels. Each is multiplied at one layer. So there are few number of kernels that form a single layer. Say suppose this layer consists of 32 filters or kernels. All these 32 filters will go through the image and will give us an output. On this output, we can perform one more thing called pooling. What pooling does is it will take we can have max pooling or average pooling. So if we have a 2x2 max pooling, we'll see in this 4 grid what is the maximum value. So 8 is our maximum value. We'll take only that. In the next thing, if we do stride 2, we'll come here. Or else if we do stride 1, we'll stay here. Here the maximum value is also 8. And in the stride, if you are doing stride 1, we'll get one more 8 here. This part is also 8. So in this part we have 1, 3 and 2. So the maximum value is 3. Similarly, if the layer is max pooling, if we have average pooling, we'll add all the things and we'll put the average value as our final output. So these two are the main kind of layers that we use. So we'll have some convolutional layer, a pooling layer, a convolutional layer, and a pooling layer. So this we can put any number of combination of layers in this sequence, and finally we'll get a list of all the information will be compressed into a single set. But all this set will finally convert that. అర్థమైందా నీకు? Okay. So we have this initial image, and we are convolving different kernel weights, and then after going through that, we are reducing the total size using pooling. So each step will decrease the number of the width and height of the image. So if we have an RGB image, we will also have the depth. So say so we have say initially we have a image RGB image. We have three images of three different colors. That will form a volume. Then we have say some 32 filters here. So as we go on increasing, see, these three images will be converted into 32 new images. With the width and height has been reduced, but the depth has been increased due to the increasing number of kernels. So as we go down this process, the total height and width of the image will be reduced, but the volume will slowly increase. So, so generally, that is the structure people follow. There are few exceptions to the structure where after doing this pooling or convolution, the image size may be persisted using just putting zeros at the corners, and the image size will remain the same. And or else there is something called unpooling that will increase the total image size. So generally the total information within the image will be compressed. After the total output, we have a fully connected layer. This will be very less. When suppose this is a 32 by 32 image, initially say suppose we have a 1080p image. So 1080 into 1080 will be roughly 10 power 6. So there are 10 power 6 connections were required to do a fully connected layer initially. But after doing this convolutional thing, we converted those number of connections into just 32 into 32. So the total number of connections will be reduced. Then after this is the same kind of classification that we previously saw. Let's go through a small example. So for this, for any deep neural network, we'll be using either TensorFlow or or either TensorFlow or PyTorch. So to give a small brief history, one of the first our libraries was Theano, Cafe. These were the initial libraries around 2012 and 2013. In 2015, Google open sourced their TensorFlow library used to do deep learning architecture development. And Keras was a free-floating library developed by Francois Cholet. He was a Google employee. So in TensorFlow 2.0, the Keras library was dissolved into TensorFlow. So within TensorFlow, there are a lot of functionalities available, but Keras is very beginner friendly and does all the required functionality. Does all the required functionalities. So Keras was dissolved into TensorFlow, and we mainly use Keras in our studies. One more popular library is PyTorch. This is from Facebook. So you generally see libraries open sourced by big companies like Nvidia, Microsoft, Google, Facebook. So they will be maintaining the repositories, and we'll just download those libraries and do our experiments. So we import TensorFlow as TF, and from TensorFlow, as Keras was dissolved into TensorFlow, TensorFlow has a module called Keras. This Keras has all the different things available for us. See. So there are different APIs for Keras, the models library, layers library, callbacks. data pre-processing, optimization, metrics, losses. Uh, yeah, so these are all the things. So we do the model building and layers. This is the model construction part. Callbacks is like calculating the errors, errors or the losses, or plotting the graphs, or saying when an epoch is completed, things like that. Data pre-processing is like converting or normalizing the data. Optimizers are the stochastic gradient descent, or mini batch gradient descent, or the Adam optimizer. This is basically the just the process by which we move from one point in our loss surface into another point. Metrics is how are we assessing our model's performance. Either it might be accuracy or it might be uh, different things depending upon the task, but generally it is the loss, sorry, accuracy that we are mainly looking into. So loss is the functions that we use, like L1 loss, L2 loss. There are different losses that you can go through, and there are some small data sets also available for us. So mainly, the main thing is the layers API. So the layers API consists of here you can see there are different things available. So so here we see the convolutional layers, con 1D, con 2D, con 3D. So till now we were seeing a 3x kernel, right? So it is a 2D kernel. So we'll use con 2D. So if you are using a volume, say suppose you are trying to do this on some video or some you might come across this X-ray volumes. So then it would be a 3D layer. If we are trying to do the convolution on some time series, we'll do con 1D. So there are different type of convolutional layers available for us. You can go through these. So the similarly we saw, right, max pooling 1D, 2D, 3D, average pooling, global max pooling, and global average pooling. What does global max pooling or global average pooling does is it will convert all the things into a single. So previously, average pooling is like a similar kernel to conv layer. It will go through the stride. It will do some stride, and it will reduce the image to a smaller grid. Global max pool, what it does is rather than forming a grid, it will just give you as a single output for the whole thing. So similarly, there are recurrent layers also available. It has some LSTM layers, gated recurrent unit layer, simple RNN layer, time distribution layer, bidirectional, convolutional LSTM layer, base RNN layer. We'll see the structure of RNN shortly, and there are a few more specialized layers. And this attention layer is the thing I was talking about, saying that it is slowly overtaking the convolutional part in images. A few dropout layers or sampling layers you can use to or increase the total size. There is also padding, zero padding, to persist the image size. So there are different merging layers also available. So depending upon the architecture, different type of layers will be used. After there are also activation layers like the non-linearity that we generally pass after doing our product. There is ReLU, Softmax, Riki-LeLU, and there are different layers available. So model building is like how would you structure the model, how to save the weights, how to load the previously saved weights, just to do some internal cooking. Callbacks is like what are do you want to do early stopping? What is the current learning rate? If you want to do some dynamically changing learning rates, you can assign learning rate scheduler, things like that. CSV logger is like where we will log everything that has happened in that single epoch. Terminate on NaN is like if we reach a no, infinite, NaN is a NaN. Say suppose we have this as our loss arena, and we started here. Sometimes when we are trying different learning rates, sometimes it is very small and will move slowly. That is fine. But if we are doing a larger learning rate, it will jump radically and we will go to infinity. This will cause an NAN. So if our model sees this kind of thing, then we will say terminate when it reaches NAN. So these are so few functionalities available for us. So this Lambda callback is like you can use this Lambda callback to create your own custom callbacks. So data pre-processing is like doing some image, some augmentations to the image. Optimizers, we have different kind of optimizers. A stochastic gradient descent, RMS prop, Adam. I would suggest you try out Adam in the initial experiments. Most probably Adam with 10 power minus 5 as learning rate is one of the best things available. A matrix is the what kind of accuracy we are trying to calculate. So you can go through these things. Mainly we'll be using mean squared error or absolute mean square error. These two things will be the general depending upon the class. So if you are doing regression, we'll use these things. If we are doing normal classification, we'll use the normal accuracy. Loss functions. So loss functions mainly depend upon the task that you have. So you have to think what kind of loss that we want. So you cannot use binary loss for multi-class classification. Binary is like 0 or 1. If you have just a dog or cat, you will use binary cross entropy. So if you have dog, cat, and some fish, then you need to use sparse categorical entropy. And it also depends on how you are trying to encode your samples. So if you have 0, 1, 2 as the numbers, then you will use categorical cross entropy. But if you have a sequence like 0, 0, 1, 0, 1, 0, 1, 0, 0, then you need to use sparse categorical entropy. You can search in Google like if you what kind of labels you have and what loss is best for your thing. By practice, you will understand what kind of loss goes in hand with your task. Okay. So here we have a few things that we imported. So let me connect to the Colab instance. So we are importing TensorFlow TF from TensorFlow Keras. We are taking the data sets. So this has our data set, the layers and models. Let's run this first part. And we are trying to download the CFAR10 dataset. CFAR10 is a small dataset that contains 10 different classes with 60,000 images. So from the 60,000, we'll use 10,000 for our test and 50,000 for our train. We are downloading and putting those things into train images, train labels, test images, and test labels. So we have classes like aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So these are the different classes of our images, and we are given a image to the model. We need to classify the image into one of these 10 classes. Let's print out and let's see different classes available for us. So we see here frog, truck. These are very small images. I think they are like 32 cross 32 images. So this is very small picture image. Generally, we have 1080p images from your phone. Generally, right? We have a DSLR. They will be a bit more larger in size. So any model should either start with a sequential format or a functional format. So it either starts with a sequential format or a functional format. So sequential is like one layer will follow another layer. Functional is like it has some loops or anything like that. So it's not a sequence. Anything that doesn't follow a previous layer, or if we are adding two different layers in between, we need to do functional. So initially, just by using sequential, it is fine. So so initially we're initiating a model with the models that we imported, and we are saying it's a sequential model. Now we are slowly adding each layer to it. So we are adding from layers. We are taking the con 2D, and we are using 32 filters, each of size 3 cross 3. And after doing this, we have a activation called relu. So this is the non-linearity. And for the first layer, we need to give the input size, input shape. So here our data set consists of RGB images of 32 cross 32 pixels. So in Keras or in TensorFlow, the filters are given at the end. So here you can see 32 cross 32 cross 3. In PyTorch, 3 will be number of filters will be given at the first, and then the shape of the image is given. So, it's a small thing that you need to remember. So if you are sticking with TensorFlow, you just give the number of filters at the end. If you are using only black and white image, it will be just 32 cross 32. You don't need to specify it, and then it will automatically consider that. If you have more than one color, or sometimes what happens is you will have RGB image and also depth map to it. Then it will be four. RGB will be RGB three filters, and the depth from the camera, from Microsoft Connect or some LiDAR, you'll have the depth information as well. So things like that. Then after that convolutional layer, we are doing one max pool layer. And then again convolutional thing, since this is not the input like layer that is facing the input, it will dynamically assess that there are 32 filters that we have to make, and it will dynamically assign everything. Just for the initial layer, we need to specify the input shape. And then at the end, we have this again the convolutional layer. Let's print out the summary. So this is our summary part. So finally, we have a 4 cross 4 image. Then there are 64 filters at the end. And then we are trying to add a dense connection. This dense is nothing but the multi-layer perceptron thing that we saw. So here we see initial shape was 32 cross 32. That is converted into 30 cross 30 into 32. Then again max pool will reduce it by 2. So it has become 15 by 15. Then the second convolutional layer, it became 13 cross 13, and there are 64 kernels. and max cooling will reduce by 2 again. So 13 went to 6. And again, we have a convolutional kernel that will convert that into 6 cross 6 into 4 cross 4. Then we are flattening that 4 cross 4 into 64. So we have 1024 numbers at the end. These numbers are connected to 64 64 neurons and then convert compressed into 10. So since we are trying to classify it into 10 different classes, we have 10 at the end. So now we are providing a compiled model. So we are saying that Adam is the optimizer that we are using. Here you can use stochastic gradient descent or anything like that. And the loss function that we are using is sparse categorical cross entropy, and the matrix is the accuracy. So finally, we are trying to train the model. So just a model.fit will do the training thing. So image training images or training labels, and we are saying that to train it for let's say for 10 epochs. So just take care that you are using the GPU provided for free by Google, so that you will save some time. So it will take some time to train the model. I have trained it previously and I'll show you the result here. So this blue thing is the uh, general training accuracy, and the orange thing is the validation accuracy. So say initially the training accuracy was 50%, and slowly after training it has been to some 80, 79, 80%. But the validation accuracy after some time has plateaued at some 676. So we can roughly say that it has plateaued at some 69% accuracy. And then we are trying to print the test data, the accuracy on the test data. Yeah, it will give us some 70%. I forgot and has run this. So after this 10 epochs are done, we will get the accuracy. I think it's almost done here. So here we can see the, so this is the label loss. Here we saw the accuracy, right? Now this will be the loss. As we keep training, the loss will go down, and the validation loss is also going down here. Yeah, so here we see that after training this, we have completed 10 epochs here. After completion of 10 epochs, we have this plot, and let's see on the test thing how much accuracy we got. We got roughly 71% accuracy. We'll also plot the loss terrain, how it goes. So see, you can see that the training loss is decreasing, but the validation loss is slowly decreasing, and after some time it has plateaued here. So we can say that after 6 epochs we can stop our training, or else it will overfit on our training. So thank you guys. So this is the same structure available for the RNN layers also. I would suggest you to go to this papers with code.com. So this has many things available as we saw in the first class. So there are different tasks in AI, and all the different tasks are shown here, and different ML papers or deep learning papers can be will be most of them will be presented here, and different benchmarks used to measure the accuracy of different papers are also available. So you can go through each and individual task that you are interested in, and browse through different papers available. Say suppose we saw that image classification is here. Different benchmarks are available here. You can download these data sets and do experiments by your own. Some data sets will be very large, and some data sets will be small. So I would suggest you